Hi everybody. I want you to just do your very best while I'm gone. All right, so this is 6.4, measures of dispersion. So measures of central tendency, we did mean, median, mode, help you explore the middle of a data set, but do not always give you a clear picture of the whole data set. The range of a data set is the difference between the maximum and minimum values of the data set. The range is a simple measure of how spread out the data is, sometimes referred to as the dispersion. Previously, we looked at the test results of 32 students. Maybe we did, maybe we didn't. I don't know. So here are the results, okay? So maybe this was a test that was 10 points, okay? So it says find the maximum and the minimum values in the range. So you guys, this is easy peasy. So the max is 10, the minimum is 0, and then the range is the max minus the min. So the range, sorry about that. This is minus 0. So the range is 10. Knowing whether the data is widely spread out or bunched around the mean provides you with a better understanding of the distribution of the whole data. You need to consider more values than just the smallest and the largest. So we're going to talk about something called quartiles. Quartiles are values that divide the data into quarters, so like fourths, 25%. The first quartile is called the lower quartile, or Q1, and 25%, and it has 25% of the data below it. The second quartile is the median, so we already know about the median. And the middle value in the data set means that 50% of the data lies below the median and 50%, that's supposed to be lies, not lives, lies above it. The third quartile is called the upper quartile, or Q3, and has 75% of the data below it. All right, we have something called the interquartile range, and it's abbreviated IQR. The interquartile range is the difference between Q3 and Q1. So in example 1, let's look at this data set. Hey, it's great. It's in order for us. So it says find the middle. Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I like to kind of write this down. There are 12 data values. So what you're going to do to find the median, remember from the last section, you just count in. So the median is the average of 36 plus 49. So that's 42.5. All right, so what that actually means though, let me use a different color here. The median is in between those, okay? The median is in between. If it had been that value, we would have put this mark on it. So the mark is where the median is located, and it's located halfway between. So then if you want to find the lower quartile, what you're going to do is you're going to then use, there's 1, 2, 3, 4, 5, 6 values. So you're going to count in 1, 2, 3. Quartile 1 is then going to be the average of 9 plus 16. So that's 12.5. So that's Q1. The upper quartile, which is Q3, you're going to take the top half, let's count in, and it's going to be the average of 81 plus 100. So upper quartile, or quartile 3, is 90.5. Then the interquartile range, so let's pick a different color. The interquartile range is the difference between quartile 3 and quartile 1. So you're going to take 90.5 minus 12.5, which is 78. The range is the difference between the maximum and the minimum. So the range is 143. So you're going to stop and let's think about this. So if I looked at the data set, the median or the middle is 42.5, but it has a really big range of 143. Okay? So it is possible to get a sense of a data set's distribution by examining something called a 5-number summary. A 5-number summary. This is the minimum value, the first quartile, the median. I think I meant the third quartile. Okay, this is the third quartile, and the maximum value. A 5-number summary can be represented graphically by something called a box and whisker diagram, sometimes referred to as a box plot. The first and third quartiles are at the ends of the box. The median is indicated with a vertical line in the interior of the box, and the maximum and minimum points are at the ends of the whiskers. So, extreme values are called outliers and might be considered for to be removed from a sample. And an outlier is defined to be any value at least 1.5 times the interquartile range above quartile 3 or below quartile 1. So don't worry, I'm going to help you with this, okay? So let's look at example 2. It says find the median and upper and lower quartiles for this data set. Then we're going to put it on a box plot and then determine whether 37 is an outlier. Okay, so let's count. How many data points are there? There are 17. So I did this on purpose. This one we had 12, and now we're going to have an odd number so you can see the difference, okay, between what I'm doing here. So now I'm going to count in 1, 2, 3, 4, 5, 6, 7, 8. There we go. So this 47 is the middle. So watch the difference here. So my median is 47. So I kind of put a bar here. So now you're going to count that I have 1, 2, 3, 4, 5, 6, 7, 8 values that are to the left. Okay, so then I'm going to count in 1, 2, 3, 4. So quartile 1 is 44. And then I'll do the same, whoops, that's a quartile 1. Then quartile 3, maybe you can see if I'm tapping in 1, 2, 3, 4. That's going to be between 51 and 52. So you take 51 plus 52 over 2. That's 51.5. Let's go ahead and do the interquartile range, which is quartile 3 minus quartile 1. That's 51.5 minus 44, so that's 7.5. All right, so watch what we're going to do on a number line here, okay? So I'm going to start 37, 38, 39, 40. Yikes, you know what, guys? Let me stop this. That's too big. Okay, wait. Let me try that again. I need to go by twos, I think, here. Yeah, there we go. That's going to go better. So let me do 36, 38, yeah, 42, 44, 46, 48, 50, 52, 54. All right, perfect. Much better. Okay, so I have a minimum that's a dot. The maximum is a dot. You're going to put a vertical bar where the median is, so that's 47. And you put a vertical bar at quartile 1. and you put a bar at 51.5. Okay, so what's interesting, oops, my dot should have been up a little higher. That's okay. Hopefully you get the gist there. So then 50% of the data is in the box. All right, now it says determine whether 37 is an outlier. So we're going to go right here, and an outlier is any value that's at least 1.5 times the interquartile. So let's compute that. And then what you do is you add that value to quartile 3. So that's what, 62.5. So there's no values above that. And then you subtract it from quartile 1, and I get 32.75. So there were no values below 32.75, so there are no outliers here. Okay? All right. Note, you need to decide whether to reject or accept an outlier. Outliers can have a distorting effect on statistical measures like the mean, but some of them are still valid data values, and it is not acceptable just to reject an outlier without a reason. For example, the heights of 15 boys are in centimeters, so they're given here. Clearly, there is an error in measurement or recording. A boy cannot be 382 centimeters tall. This is an outlier and should be discarded. So that's kind of the understanding I want you to get. Suppose test results of 7 students are 20%, 22%, 18%, 30%, 26%, 89%, and 21%. If the data is checked and the student who scored 89% was not error in recording, then this has significant effects on the conclusion that you draw. Without the outlier, a teacher might conclude the test was too difficult. With the outlier, the teacher might also conclude the test was fine, but that 6 or 7 students did not study appropriately. So teachers use this kind of information as we look at our assessments. So I hope you know that. I really do look at them. All right, example 3. A group of 80 athletes each run laps of a running track. The grouped frequency table shows the number of laps run by different athletes. So we have 0 to 10 laps, there was 1. 10 to 20 is 20. 20 to 30 is 31. 30 to 40 is 21. And 40 to 50 is 7. So what we're going to do is we are going to look at something called a cumulative frequency, okay? So what you're going to do is we're going to call it CF. So after the 0 to 10, there's only one person who had done that. But then a cumulative frequency means I'm going to add each subsequent value. So then if I add 31, that's 52. If I add 21, that's 73. And if I add the 7, that's 80. So if we want to construct a cumulative frequency table for this data and use it to draw a cumulative frequency curve for the number of laps run by different athletes, we can do this. So watch what I'm going to do here. Okay, let me see how much space I have. There we go. And notice I'm only going to be in the first quadrant because you can't have negative number of laps. It doesn't make any sense. And notice how I am labeling this. So I have my x-axis is number of laps, and the y-axis is the cumulative frequency. So let me change colors, and I'm going to plot. So at the end of 10 laps, we have 1. At the end of 20, we have 21. At the end of 30, we have, what, 52. At the end of 40, we have 73. And at the end of 50, we have 80. So you can kind of tell what's happening here, okay? So it says, use the curve to estimate the median and interquartile range of number of laps. Okay, well, let's take a look at this. It says you're going to plot the cumulative frequency against the end point of the data class. So the median is the 80th divided by 2. That's going to be our best estimate. So it's the 40th data value. So we're going to do kind of an estimate here. So it looks like that's about 26 laps. Okay, so what you do, so again, to find the median, we're really looking for the middle. So the cumulative frequency was 80. So the middle would be halfway. So I took 80 divided by 2 to get the 40th, okay? The 40th data value. So now, if you want to do quartile 1 would be a quarter of the data. So you would take 80 divided by 4, which is 20. So let me use a new color. So if I go to 20 and hit it, I don't know where that is exactly. Does that look about? Okay, on the one I did on mine, it looked more like 20 than it is here. So I don't know. I'm gonna go with what I have here. So I said quartile 1, the 20 went with the 20. Okay. And then quartile 3 would be 60th. So if I go up here to the 60, I got about 34. So the and again, like you're eyeballing this and you probably would use graph paper and it would turn out a whole lot better. So the interquartile range is going to be 34 minus 20, which is 14. I got the median. This was the median. Okay, there we go. All right. All right, a percentile is a number where a certain percentage of scores fall below that percentile. If you score 64 out of 80 on a test, you do not know how well you have done unless you compare your score to the whole class. If you know that your score is in the 90th percentile, that means you scored better than 90% of the people who took the test. The mean is often called the 50th percentile. The lower quartile is called the 25th percentile, and the upper quartile is called the 75th percentile. The variance is a measure of how far, on average, each data value differs from the mean. So let's consider the 32 test results. The variance would tell us whether students' test scores were, in general, close to the mean average score or far away. The variance of a data set is calculated by taking the arithmetic mean of the squared differences between each data value and the mean value. So I'm going to show you how to do this by hand, and it's awfully, awfully tedious, okay? And then I'm going to put a video on the module to show you how to do it with the TI Nspire, okay? So it says find the mean. So the mean, we use the x bar, is the summation of the x values over n. So I've done this, so I did 168 over 32. So the mean is 5.25. Now what I want you to do, and I'm going to see if I can make this big enough for us. I want you to, we're going to do several columns here, okay? And this is going to be like super, super long. Is we're going to first do x minus x bar, and then we're going to square it. And then you'll see why in a moment, okay? So the first thing you're going to do, and this really is super tedious, and I need to double check because I think that on the IB exam, they let you use the technology, which would be way better than this. Okay, then I did have to make another table here. Okay, again, this is going to be like super duper tedious, okay? So just bear with me as we do this. All right, so what you're going to do is you're going to take the x value. So if I do 0 and then I subtract 5.25, that's negative 5.25. Then you're going to square it, okay? So that's 27.5625. Then when you take 1 minus that, it's negative 4.25. Well, then that's going to repeat, right? They're the same. Then you're going to notice once I get rolling, I'm not going to write it out all those times. So then for the 2, that's negative 3.25. And then I got lazy. Okay, so then I said that's 10.5625. And I drew an arrow like you get it. So then when you do the 3, it's negative 2.25, which was 5.025. So you're going to do that each time. And then I got negative 1.25, which is 1.5625. Then we're going to go down to where the 5 is. So you take 5 minus 5.25, and if you square it, so remember, negative squared become positive. Then when I did the 6, I got 0.75, that's 0.5625. For the 7, I'm not going to write it all those times, but then I got 3.0625. For the 8, I got 2.75, and when I squared that, I got 7.5625. For the 9, I got 3.75, that's 14.0625. And for 10, that's 4.75. I got a 22.5625. All right, and so just keep in mind, I really am supposed to be writing those out, but it's a pain. It's a literal pain to do that, okay? So this is super tedious. All right, so what I just did is we subtracted and we squared. Okay, so now why? Why did we do it? Well, the variance is called sigma. This is a sigma notation, okay? That's sigma. And what you do is you add up all the squares, okay, so that's in that far right column. We're going to add up all those together, and thankfully I did that already, and I got 198, and n is 32. So the variance is 6.19. The mean divided by the number, it's the sum of the squared distances from the mean divided by the number of data values. So note, because the differences are squared, the units of variance are not the same as the units of the data. Therefore, statisticians often find what's called the standard deviation. And the standard deviation is the square root of the variance. The units of the standard deviation then are the same as those of the data set. So then all you do is take the square root of that. So the standard deviation, and sometimes it's referred to as SD, so SD, standard deviation, is the square root of your variance. Okay, that's what that's saying. The standard deviation shows how much variation there is from the mean and gives an idea of the shape of the distribution. A low standard deviation shows that the data points tend to be closer to the mean than a larger standard deviation. So here's some properties of the standard deviation. Standard deviation is only used to measure spread or dispersion around the mean of a data set. Variance, and therefore standard deviation, is never negative because it is an average of the squared distances. Standard deviation is sensitive to outliers. A single outlier can raise the standard deviation and in turn distort the picture of spread. For data with approximately the same mean, the greater the spread, the greater the standard deviation. All right, example 4 says a data set has a mean of 12 and a standard deviation of 2. Each value in the data set has 20 added to it. Find the new mean and the new standard deviation. Well, the standard deviation stays the same. Okay, the standard deviation stays the same. However, the mean, all the values have had 20 added to it, so the mean is 32. All right, each value in the original data set is multiplied by 4. So we're still coming back up here. Find the new mean and the new standard deviation. Well, the mean has been multiplied by 4, so that's now 48. But because I did multiplying, the standard deviation is in fact multiplied by 4 as well. All right, that ends the video.